Hello, and welcome to the video lecture for topic 22, 1-2 and 1-4 addition to conjugated dienes. So, dienes are, just as their name implies, di for two, ene for alkene. This is a molecule that's going to have two alkenes in it. And we're going to limit our study of conjugate addition to conjugated dienes. Now, a conjugated diene has a carbon-carbon double bond, a carbon-carbon single bond, followed by another carbon-carbon double bond. This is a conjugated diene. And these are the systems that are going to be the focus of topic 22 and this video lecture. So, similar to standard alkenes and alkynes, our conjugated dienes also participate in electrophilic addition reactions. And for the most part, they obey very, very similar rules. So we'll just take a simple example, right, at the addition of HBr across this diene to start off. So the first thing that we need to take into consideration is which alkene carbon is this hydrogen atom going to add to? So, if I add it to this alkene, I can add it to this carbon, which I'm going to call 1, or this carbon, which I'm going to call 2. So let's take a moment and see what the result of those two different potential additions. Right? If I add it to carbon 1, so here now I've added the hydrogen to carbon 1, that means I form a carbocation on carbon 2. We can classify this as not only a secondary carbocation, but is a secondary allylic carbocation. If I were to add to carbon 2, there's the hydrogen atom that I added, that would leave me with a primary carbocation. And it's not even allylic, so this is a very unfavorable carbocation for us to make. As we know, primary carbocations never form. So even though I'm adding to the more substituted alkene carbon, even though I'm adding to the less substituted alkene carbon, right, I am still creating the most stable carbocation. So this is still following Markovnikov's rule. Once I've generated that allylic carbocation, though, I should recognize that it can undergo resonance. So, again, we think of alkenes as a weak base. So this is an acid-base step, and we use equilibrium arrows. Now, in terms of resonance, we can delocalize that positive charge from a secondary allylic carbocation to a primary allylic carbocation. Now, from this, we can generate a resonance hybrid that looks like this. And we know that we're going to have partial positive charges on carbons 2 and 4 if I continue with the numbering scheme I used for my protonation. So the next question we need to ask is, which of those two is going to carry more of the positive charge? Is carbon 2 going to carry more partial positive, or carbon 4 going to carry more partial positive? And that goes back to the nature of each of these resonance structures. We know that a secondary allylic carbocation is more stable than a primary allylic, so we're going to have a larger partial positive on carbon 2 and a smaller partial positive on carbon 4. Finally, this is going to allow us to take a look at the two different products that we can form. So I'm going to start from the carbocations. Here now is our, secondary allylic carbocation. And I'm going to number the carbons 1, 2, 3, 4. Here's my bromine nucleophile generated in my first step. And that nucleophile can add to carbon 2 to give this product where we have added hydrogen to carbon 1, we have added bromine to carbon 2, and we formally call this the 1,2 product, or the 1,2 addition product. If we take a look at our primary allylic carbocation, there's the hydrogen I added in my first step. There's my positive charge. Here now my bromine can now add also to that primary allylic carbocation to give this product, where I have added my hydrogen to carbon 1, my bromine to carbon 4, and created what is called the 1,4 addition product. Okay, so let's think about these two processes. Considering our resonance hybrid, the majority of that partial positive charge sits on carbon 2. So we can think of carbon 2 as being more positive than carbon 4. This negatively charged nucleophile is more attracted to the carbon that has more positive charge. And so it's very fast for this bromine to react with carbon 2 and give our 1,2 product. This is very fast. However, if we compare our two products, my 1,2 addition product gives me a monosubstituted alkene, versus my 1,4 product, which gives me a disubstituted alkene. So in terms of the product, my 1,4 product is more stable. And so now we can begin to talk about, we can use another set of terms, kinetic versus thermodynamic, to describe these two products, right? So because my 1,2 product forms faster, carbon 2 carries a larger partial positive, my negatively charged nucleophile is more attracted to that larger partial positive. This process, my 1,2 process, occurs faster. We can call this the kinetic product. However, my 1,4 product produces my more stable alkene, so this is going to be what we call the thermodynamic product. Right? So kinetic product only refers to the process, where thermodynamic only refers to the product. Right? Kinetic, how we got there. Thermodynamic, what we ended up at. So these two labels, right, are in addition to 1,2 and 1,4. Kinetic product being the product obtained through the faster process, thermodynamic product being the product that is the most stable. So that's pretty much all that I have to give you on this. The last thing that I want to say in terms of 1,2 and 1,4 addition is you never know which one's going to be kinetic and which one's going to be thermodynamic. You need to do this resonance hybrid analysis from your initial carbocation, draw the resonance structure, see which one is the better resonance structure. In our example, it was the secondary allylic was better than the primary allylic. Assign the different magnitude partial charges, right? Draw out your 1,2 product, draw out your 1,4 product, see which one of those is the more substituted, that's your thermodynamic. Then see which one of those arrived from the larger partial positive in your resonance hybrid, that's your kinetic. Sometimes your 1,4 product might be your kinetic product. Sometimes your 1,2 product might be your thermodynamic product. Sometimes the 1,2 is both the kinetic and thermodynamic product, right? Don't make assumptions during this process. Work it out step by step and really make sure that you see which one came from the larger magnitude charge, which one forms the most substituted alkene, right? This is how we're going to be able to determine kinetic versus thermodynamic. Make sure that you're numbering correctly. whichever alkene carbon you add that hydrogen to, that's going to be carbon 1. Whichever carbon the nucleophile bonds to will be either 2 or 4. All right, this was a short one. I hope it was a sweet one. I hope that you guys benefited from this. This is one of our easier, more straightforward topics, hopefully. The only trickiness comes in determining kinetic versus thermodynamic product. All right, as always, thank you for watching. If you have any questions, please bring those to conference, office hours, lecture, or make an appointment to see me one-on-one. Thanks a lot.